Number 39. Good evening and welcome. Any quick questions or comments before we dive right into chapters 15 to 19 and wrap up book number 1? If we wrap these chapters up tonight, we will, no problem. They're not long, big fat chapters. There's some stuff in there, but you're going to learn it. You're going to review it. And we're going to review it all again starting on Thursday. So piping and materials, and a little bit about connecting piping and materials. The next chapter is steam traps. So the things we're going to connect to piping if it's steam piping. And just saw a little video on water hammer. The sort of close, more destructive relative of water hammer is called steam hammer. And too much water accumulating in a steam pipe will cause those destructive kind of forces and literally wreck equipment and break pipes apart. And I've seen it happen on big systems. So it is not fun. So I've clicked on something on this PowerPoint. It is not what I want it to be on. So there we go. And it goes right back to the beginning. Back down. Lots of stuff, eh? Okay, I found my groove. So here we go. Piping, chapter 15. So we have small pipes and big pipes. Most pipes are made from steel. There's 2 little memory bubbles on the side of that statement. Here's some pipe being manufactured. On the right and on the left, we have a typical factory out there with all kinds of piping. So common piping materials, things like steel, cast iron, brass, and copper. More and more, we have plastic type materials now. I worked in a plastic factory for a long time. I'm not even going to begin to explain what these different names for plastic mean. It's a whole world of science all in its own. Typically in the plants that we're going to work in and talk about and see, we're using steel. Different kinds of steel piping. There is cast steel piping. There is a couple categories, welded or seamless piping that we're going to actually talk about. We're going to leave the cast steel piping alone. Steel pipe comes in seamless or welded type. Cast iron pipe, we'll mention it briefly. It has high resistance corrosion, and we know that from talking about cast iron used to build cast iron boilers. Sometimes brass and copper. When I originally started working in these big plants, the control instrumentation connection of choice was a tiny little 1/4-inch copper tubing. Copper is an interesting material. One of the things about copper is it does not handle high temperature very well. And the other thing is, if you work in an ammonia plant and you have exposed copper, the ammonia from the random leaks that occur from time to time in an ammonia plant will destroy the copper in very short order. So copper and ammonia are reactive, and Very rarely is copper used anymore in industrial settings. We've switched it all over to stainless steel. But if you remember that copper does not handle temperature very well, from page 15-4, and remember that it's typically used in plumbing, certainly in the plants we have plumbing, and you'll see some copper. A lot of the copper in plumbing has now been replaced with various forms of plastic. Commercial pipe sizes. So you're going to have to find out a little bit about pipe sizing. Well, there's a big 2-page chart on page in chapter 15. I think it is 15.5. 15. Boy, we're well into the book. This is a good thing. 15.6 and 15.7. The old book was 15.4. So a couple pages full of numbers. I'm going to remind you for future use, there is a chart like that in your academic supplement. Does anyone have the page flag to pop it open? My index in my academic supplement, I've made a few notes. I guess I can't. I have a document camera, but it won't work on my newest computer. So underneath fluid mechanics, between page 30 and 33, I made a note that the pipe chart is on page 32. We'll be referring to that chart a bit in the chapters tonight. So if you carefully have a look at that chart, you're going to see that there's different sizes and different thicknesses. And pretty important to remember, there's weight in the chart. There's 2 numbers in many of the squares on the chart, and there's a note. Upper figures are walls thickness in millimeters. Lower figures are mass per meter in kilograms. So if we look up a piece of 12-inch pipe and it's standard piping or Schedule 40, its thickness is 10.31 millimeters, and the weight of that stuff is 79 kilograms per meter. Just to give you a short lesson on looking up a piece of pipe in the pipe chart. Back in the day, we used some sizing that went like this: standard, standard pipe, extra strong pipe, and double extra strong pipe. And a more modern, one of your exam questions talks about a modern method of designating pipe wall thickness, and they call it schedule number. Well, this actually came in 1932. So some of you were here at the beginning when we talked about old school things in the, they're calling something invented in 1932 as a newer method. Notice on your academic supplement, actually, well, it's not in the textbook, but in the academic supplement, when you look at that piping chart, we'll talk about this, page 32, page 32. And if you don't see a bold line, I'm going to try. Okay. So see the bold line across my pipe chart? Oh, we lost the focus. I'm going to, I have a slide in here that'll point that out. So if you want to know the pipe wall thickness of piping, you're going to use that chart. You're going to see across the top on the second page of it in the textbook, the old school standard extra strong and double extra strong. That schedule number across the top in your academic supplement. And you'll note that up to and including something called DN 300 or 12-inch, the size is expressed as nominal inside diameter. The actual outside diameter is pipe size is higher than that, so 14 inches and higher. Okay, and we'll have a look at the chart and I'll point that out. So 2 systems, according to the textbook. One system used to be called S, XS, and XS. So you could have standard pipe, you could have stronger pipe, and you could have really strong or really thick piping. Okay, now we've got schedule 20, schedule 30, 60, 80, 100, 120, 140, 160. Normal, to correlate the 2 systems, standard is schedule 40. Okay, there's also a schedule 10 on the chart. This is thin stuff for plumbing and home projects. When we get into some serious pressure in our piping, we're going to be using schedules like this. Okay, this is all from the pipe charts in your textbook. So schedule 40 is standard pipe. As we go from 10 across the chart at the top over to something like 160. It looks like double extra strong is even thicker than 160 by about double. Just looking at scanning the numbers of thicknesses there. So larger schedule number. So if you have a 10, it's cheap thin piping. If you have a number 40, it's considered standard piping. And you go up to a higher number, this is the real deal, the thick stuff, okay? Back in the day, we referred to pipe by these things, standard extra strong or double extra strong, and the new system from 30s or 40s is schedule numbers, starts at 10, goes up to around 160, or on the charts that we have anyway. All classes or schedule, so a class 10 is the same as a schedule 10. A class 40 is schedule 40. A class 120 is schedule 120. So classes called schedule. If you go across the chart, you pick a size. For example, I'm going to pick 8-inch. So there's an example here that doesn't say what size, but it says 168.28 millimeters. So if you look at the chart, column number 3, outside diameter in millimeters. So outside diameter in millimeter, 168.28. Who wants to tell me the size of the pipe?
6-inch.
It's a 6-inch pipe. We would call that classically a 6-inch pipe. And the metric equivalent, or DN, so I had a student ask me early today, what does DN mean? And I said, you know what, I have no idea. And we looked it up together, and it's basically backwards terminology. It's digital number. Well, that's the simplest translation. So if we have pipe that's 150 millimeters, we can call that a 6-inch pipe. If we jump down to 8-inch and then look across, you can see you have numbers for our schedule 20, schedule 30, standard wall. Thickness is 8.18 millimeters, and then the number there, 42.2. If you look at the note at the bottom of the page, that's the kilograms per meter of 6-inch standard wall or schedule 40 pipe. Okay, and if you examine the numbers closely, up to 12, and then my academic supplement has a bold line across between 12 and 14. And if you don't have that bold line in your supplement, I recommend that you add it in. And when we get to that slide, I'll show you exactly what that means. How do we, let's just find that chart. Where is that chart? Did that chart disappear? Here we are. So please open your academic supplement. And I'm not sure if you can tell this line. It should be bold. If it's bold in your academic supplement, that's good. If you have a different version than I do, I've seen them without this bolded line. Take a highlighter, draw something across there, because it's important to know what happens when you go from 12 to 14 and bigger. Okay, there's a couple possible questions on making sure you know where that line is. Okay. Piping. How do we hook pipe together? 3 ways that we're going to talk about. Threaded or screwed fittings. We'll have a closer look at what that is. Often we use flanges, flange connections, and often piping is simply welded together. All the pieces are lined up. We have welders come in and hook things together for us in a permanent fashion. Flanges and threaded are somewhat popular because we can actually take it apart. Piping will often need to be taken apart. But if we have something like a gas fuel line where we must not have leaks or minimum amount of leaks, we're going to weld things together and ensure that it's all tightly joined on a permanent basis. So threaded piping and screwed fittings, generally in smaller sizes we do this. The gas line into your furnace and hot water heater in your basement, you're going to see it's what we call carbon steel piping. It'll have a black coating on it. Sometimes it's a gray color. And pieces of pipe are cut and threaded and fit together. There's unions and different kinds of things. We'll have a look at them. And this can easily be assembled and disassembled. Should the time come along that you need to have the furnace replaced, the right qualification, a guy can come in and take it all apart without any welding in your basement. This disadvantage, when we thread a pipe, we take away the strength of the material because we remove thickness. And the next picture will. So by threading the end of a pipe, we have a thickness of pipe wall that allows us a certain amount of strength. And then where it's joined at the end, we have to cut progressive threads out of it, and we end up weakening the whole system, because any system is as strong as its weakest point, correct? Threading process cuts into the thickness, reducing the effective thickness. So we literally have to make the piping way thicker than it needs to be so that at the threaded point it's strong enough for our system. Other fittings we'll briefly look at, things called elbows, things called nipples, things called couplings, and things called unions. And we'll have a look at a bunch of fittings. Here we are, coupling. So coupling, we can take 2 pieces of threaded pipe, thread them in to either side and hook them together quite easily. If we need to tap in or tap off, we have reducer tees or normal tees, and then if we got to go around the corner, we can put in elbows that are 90 or 45. Sometimes the elbows can be made with what's called a male thread on one end and a female thread on the other end, so we can join a fitting to the end of a pipe and go around the corner. Nipples will join fittings together. Return bend if we have a reason to go around a corner 180 degrees, and bits and pieces like this. And as we get to, I'm looking for this, I'm looking for a union. When we get all the pieces hooked together, we need to hook it to some existing piping. Generally, we put in a union, and this is a joint that allows us to take out a piece or a part of the piping network for disassembly. Cutters and threaders, so the chapter will show you some bits and pieces for being able to cut your pipe with cutter. We can put some dies in a ratchet or a handle and carve those threads into the end of the pipe and build ourselves a nice system. Sometimes we have power equipment to do it. Sometimes we have handheld equipment, but we're not going to teach you how to build a piping system. So that was threaded piping. Flanged connections. One part of the chapter calls this a loose connection, something that is separate to the pipe, and we put it either on the end of the pipe or we weld it to the pipe. And each section of pipe has a flange on the end, fits with flanges from other parts of the piping. We're going to look closely at three kinds of gaskets, three pipe flange gasket types: full face, ring joint, and flat ring. There's descriptions and pictures in the text. We'll look at them briefly. When we get to chapter 19, we're going to talk about very hot oil in a system. Hot things leaking out of a system are bad enough, but if it's hot oil, it's very likely to cause a fire that's hard to put out. Burning fuel type fires are extremely hot, fast spreading, and hard to put out. So for those specific kinds of devices, we're going to use metallic gaskets, and we'll look at what they look like. Favorite brand name, Flexitalic. Some of you are familiar with that. And that's for high temperature service. If we use a flanged or flange connection, we can assemble and disassemble. And it's actually a lot easier than screwed connections, especially if we have larger sizes. Turning big pieces of pipe and big fittings around getting them threaded together tightly is quite the process. If we have flanges, we take out some bolts and bring every piece of pipe apart. Some types of flanges, there's weld neck flanges, so welded onto the pipe, welded slip-on flange, and some flanges are screwed onto the piping, and another type called looser or lapped. Different gaskets that are used in flange connections: full face, ring joint, and flat ring. Remember that flanges can be welded neck type, welded slip-on type, threaded. Another word for threaded flanges is screwed. And loose flanges is another method. Here's a reminder, there's three kinds of flange connections: weld neck, welded slip-on, and screwed or loose lapped. And there we are. There's a welded flange welded onto our piece of pipe. Here's something called a lap joint. So we welded an end onto the piping that has a flange. And this loose flange is on the outside diameter of the pipe, and it moves around and rotates so that we can have an easier time of lining up our bolt patterns. And then some flanges just simply are threaded or screwed onto the end of the piping. When we use this kind of pipe connection, these flanges, we're going to need something to prevent leaks, and we're going to use gaskets. Flange connections use gaskets to prevent leaks. It's simply gaskets squish or squeeze into the imperfections. Every piece of metal, even if it's shiny, if you look at it under a microscope, you're going to see some flaws or scratches in it. And if we put two metal faces together, it's probably not going to be leak-free. We're going to need some kind of soft material in between. And some gaskets are not really very soft. We'll look at a ring joint gasket. Remember, the ring joint gasket has an oval shaped cross section, and here it is. So ring joints look like this. So this is the one side of a flange. This is the other side of the flange. These flanges are bolted together. And this is a high pressure installation. They use an oval cross section ring joint gasket. So here they are in different sizes. Other flange types with different gaskets. If we have a flat face flange, the gasket is called full face. Notice that the full face means it goes from one face all the way to the outside edge. And because of that, it must have bolt holes, so the bolts could go through the gasket. Some flanges that use the ring joint with the oval cross section, the gasket fits in a groove in the flanges, and when the bolts go through, they are exposed. So if you look at the edge of a flange and you see I wonder if this next picture helps. Yeah, if you see this gasket on the outside edge of your flanges, this is going to be a full face gasket. Okay, so that's this one. Important to note the cross-sectional profile of the ring joint. A flat ring gasket works on something called raised face flanges. So these flanges come together and you'll see the bolts exposed, and the ring joint gasket will only cover the raised face. Sorry, the flat ring gasket will only cover the raised face. Another kind with narrow flat ring gasket, and another kind with narrow flat ring gasket. When you use flanges, you use gaskets. The faces and gasket must be clean. Faces must be aligned, and that's what prevents leaks. Any imperfections in gaskets need to be usually new and good shape. If there's cracks or scratches in the gaskets, they're going to leak. Important to tighten flanges correctly so that they line up perfectly flat, come together evenly. And if they're square and flat, this will ensure the gaskets are flat and doing their job and not getting crimped or damaged. Important to know that if you tighten bolts on a flange in an effort to put them together squarely and evenly, you need to have a sequence, and there will be specific sequences. If you have a 4-bolt flange, you're going to go use a crossover or crisscross method. You're going to start with number 1, number 2, go to 3, go over to 4. When you tighten up the stud nuts on your vehicle wheels, you should use the same method. You tighten the hand tight in a crisscross pattern, and then you use that recommended pattern again to go to about 1/3 of the maximum torque. Use the pattern again to go to 2/3, and then depending on the procedure, very high pressure flanges with numerous bolts will go up to 90. It'll be a 4-step process, 90% of maximum torque, and then again to the 100%. If you work in critical industries with very high pressures and, for example, nuclear power plants, Each bolt, each pass around the flange to tighten the bolt will have to have your signature or your initials on a piece of paper. Some of you have seen this before. And somebody else will come and witness you tightening that bolt the right number of times, the right number of pounds of torque. You fill it all on a sheet. There's going to be from 6 to 18 different signatures for each bolt to say that it was correctly put together. And we still have things coming apart. Okay. So if there's an important procedure, it's there for a reason. Okay. We want to follow the crisscross or crossover method. This makes sure that our flanges are tight and leak-free and going to stay tight and leak-free for the longest possible time. Welded connections, pipe lengths are welded to one another. Fittings and valves are welded in between the pieces of pipe. If welded, there's less likelihood of leakage. Weight is reduced. We don't have all these heavy chunks of metal at every joint. So less maintenance. Of course, you don't have the ability to do maintenance if you have to cut apart a welded piping system. You often have to start over when you put it back together. Plus, are generally less material and labor. The joints are smooth, can be made perfectly unnoticeable, so easy to insulate and clad the piping. More flexibility to design. You can design whatever you want and a welder can build it for you. Disadvantages, only qualified welder can make the connections. Something called socket weld, smaller piping under 2 inches is generally put together where there are fittings. They have a friction fit together and then they're welded to seal. Socket welded. Piping under 2 inches is usually socket welded. When we're socket welding or welding piping together, we use something called backing or backup rings. They're just part of temporary installation to line the pipe up for, we could be working on 12-inch or 24-inch or 48-inch piping. Welders could be working for days on one of the piping joints. So things to make sure things are aligned. So this already is a quick review of chapter 15. What is the most common material for pipe that we're going to see?
Steel.
Some kind of steel. There are all kinds of steel. What kind of steel is most common? It's piping made out of steel. Okay. Might be cast or welded or seamless pipe, but most often we see steel. Cast pipe would be for resistance to. Cast iron is cheap, not good for temperature, not good for, cast iron is brittle, not good for extreme pressure, not good for lots of pressure, but it's good for corrosion. Main categories of piping.
Welded and seamless.
Yeah. Okay. Copper and copper alloys, things like brass, not suitable for high temperature and generally just used for plumbing. Not to berate the use of plumbing, we all need to have plumbing. We'd be, we had water off here for 3 days. It was not a fun 3 days. Old system, double extra strong. Pipe had standard thickness, extra strong thickness, or double extra strong, meaning thick. We have a new system called schedule. And you'll see piping from 10 to 20 to 40 to 60. Which one is equivalent to standard?
Skid 40.
40.
Skid 40 or Schedule 40, correct. Remember, in the thickness tables, you can determine the actual size and also the weight. Important to be able to know the weight of piping when we're talking. We looked at one, I think was 72 kilograms per meter. 20 feet, 6 or 7 meter lengths of pipe. 20-foot length of pipe, what do they call that now? 7 meters or 6.5? Pipe fitters out there?
6 meters.
6 meters. So 6 meters of 72 kilograms per meter, you're probably getting a complicated permit for a heavy lift every time you have to move one of those puppies around, right? So remember this number, 12 inches on your pipe chart. There should be a line. And then the next number on the chart would be 14. And up to that line, the inside diameter is actually the nominal pipe size. A 12-inch pipe will have a thickness at Schedule 40. And at Schedule 60 or 80, a thicker 12-inch pipe, it's going to be thicker and the inside diameter is going to be less. So when we build with thicker piping, we need to remember that we're reducing the diameter. We might have to go to a larger inch pipe size or DN for digital. All classes, so going across the classes, 10, 20, 30, 40, or standard or extra strong, the same outside diameter as across the page in the pipe chart. And there's your chart with all the lovely numbers. So as pipe wall thickness increases, what happens to the inside diameter? It gets less. Thicker pipe, but less space to put the liquid through the pipe. Schedule 40 pipe, standard pipe wall thickness up to 10 inch. So up to 10 inch, the thicknesses are equal, standard wall and 40. Beyond 10 inches, it's somewhat different. What happens when you thread pipe? Not a favorite method for industrial piping.
Wall thickness is reduced.
Correct. Yeah. We don't want to have weaker pipe. Different kinds of connections. We have screwed or threaded. We have loose or flanges, and also welded. So a different version of the same conversation. We attach pipe with welding. We attach pipe with flanges. We can use screwed fittings, and we don't use those things. Ring joint gasket has an oval cross section. Okay. What about 2-inch and smaller piping? Usually socket weld. Backing rings, they're there to align and support the pipe while we do the welding. Tightening flanges, very important to remember, use a crossover or crisscross method. Any questions on piping in chapter 15? We're going to be talking about piping all the way through these chapters tonight, so we'll be revisiting some of the stuff. All good, everybody's happy. Okay. Rob, are you still having trouble?
No, I'm back on. I had trouble at first. Nothing was live but the audio, but I just logged everything out and updated my computer and logged back in, and I'm good to go.
There you go. Sometimes those updates make you crazy. Once a weekend, I try to shut everything down and update everything. If I don't, I get into trouble. I get a crash. So within piping, piping runs can be a couple feet long. They can be 1,000 feet long. They can be many kilometers long. So we're going to learn and talk about metal, such as steel piping and other things, anything that we make anything out of. We're going to put something in it. We're probably going to put something hot in it. It might be something very cold that we put in it. We'll talk about that too. And that thing that's many miles long is going to grow. A meter of pipe is heated up a few hundred degrees. The length might change a couple of fractions of a millimeter. If that piece of pipe is a mile long and we heat it up to 300 degrees, we put 100-pound steam in it. It could grow by a few inches. So we need to soak up that expansion, absorb it, because steam pipe goes from a boiler house over to a power plant or a building to be heated. It's a mile long and the pipe gets longer and shorter. A couple times a day, things are going to be stressed and strained. So we're going to talk about how to support the pipe so that they can move around, and we'll look at expansion bends and expansion joints. And then we'll talk about insulation, keep the heat in. So as piping is heated, it expands. Length change causes stress on the piping and on the connections and on the equipment that things are connected to. If we use expansion bends, and we'll also talk about expansion joints, that will reduce the stress. And if the piping is very high pressure, usually you're going to see bends like this. Joints will be more possible places for leakage, but we'll look at them both types. Pipe is cooled, so heating it up will cause it to grow, and when it's cooled, that means it will contract or get smaller, so we need to have something built in to absorb that. So if you've ever been walking down a roadway in a plant, you'll see what we call high lines. Generally, they'll run along the side of the road, or there'll be a road beside a high line. Chicken or the egg, I'm not sure which. Probably the road was built and they used the road to build the high line. All of a sudden, you're going to see the piping cross over the road, go around another corner, and then come back across the road and keep going. Well, that's an expansion bend. Okay, when that pipe gets longer and shorter, it can just move a little bit. Nobody's ever going to see the difference, but it can be 5 or 6 inches. I worked at Dow Chemical outside of Fort Saskatchewan a few years back, and plants there, from my central maintenance building, I worked in planning and central maintenance. It could take me 45 minutes to drive out to the farthest plant on site. And piping came from the utilities plant all the way out there, and 4 or 5 miles, I'm sure, at least 4 or 5 kilometers. So lots of these bends where the piping went along the road for a while, then across the road and in a loop and back across, to ensure that minimal stress. Another method, sorry, go ahead.
I don't remember seeing those at Christina Lake.
Yeah, that was an interesting setup. The long pipe runs out to the wellheads. We're literally laying on the ground.
Yeah, it's weird.
And did that run a pipe go straight out to the well? No, it was bending and curving. And some of my operator friends that went there 20 years before I was there, they said they saw those pipes jumping off the ground 3 or 4 meters in the air when they were hammering the steam out to the wellheads. Yeah.
Well, it's on pilings now, so I imagine there is some like where it's just sitting on like, I guess a piling with a couple cross piece of angle iron where it can slip on there maybe, I guess.
Yeah, and we'll look at those kinds of things
Okay.
in this chapter actually. So another thing is something called a slip joint or expansion joint. So 2 kinds of expansion joints. One called a slip joint. This is a slip joint. A piece of pipe goes inside another piece of pipe. And the bellows type, so corrugated type. If they're slip joint, there's some packing in here to prevent leaks. Is it always perfect? Maybe not, right? This kind is a solid structure. It's just got some bends in the sides of the piping to allow it to compress. So bellow or corrugated style expansion. And somewhere in the textbook, it tells you this. These particular ones are good up to 2000 kPa, so fairly high pressure. And there's a bellows type on the next page, 2000 kPa. Corrugated type for lower pressure. Lower than the highest pressure. If you have extremely high pressure systems, you want to just go with piping and put some bends in the piping. Okay. And due to the weight of the piping, the fittings, insulation, and whatever's in the piping, prevent damage to equipment. We need to support the piping, and that doesn't mean attach it or hold it down. Certainly in certain places you're going to hold it down, but you need to allow that movement. So supports will allow for free movement as the piping expands and contracts. So different versions of that. Hang the pipe from a ceiling with a hanger. Fancier ones are clevis and hangers. So these are supported up to ceiling with a bolt or a cable. And then if the piping is moving, this can swing just a little bit, enough to take up the movement in a medium or short run of piping. If we have more movement, if we're expecting quite a bit of movement, we'll have something like this with a roller in it so that it can move along. There was mention of a pipe out in the tundra, a large piping sitting on a piling. Probably you'd see a roller like this so that could move around. Occasionally you'll see something called an anchor chair. You might want the expansion to go in a certain direction. So you would add an anchor chair to support it and hold that particular part of the piping still. And then we've got some snazzier ones. We'll look at them a little closer. So on this slide of particular interest, adjustable roller stand. So this is for axial movement. Okay, the pipe is laying on this stand and it's moving this way and that way. Anchor chair. So this is a method to anchor the piping. Keyword anchor. Hold it still, hold it down. A couple different kinds here. Ring hanger, the clevis hanger, the roller chair, and the roller hanger. So you can see there's something round that allows this piping to expand and move back and forth. Okay. Constant support hanger is on page 16-7. If the horizontal piping needs to have vertical movement, so if this piping went along and then it went this way, so this pipe is horizontal up here, but this piece of pipe is going to expand and contract and cause a little movement this way. So we're going to use something called a constant support hanger. Used to support horizontal piping undergoing vertical movement due to expansion and contraction. Kind of the neat thing about these is there will be pipe inspectors in your plants that are big enough, and they are literally inspecting and checking all sorts of things all the time. There's indicators in these hangers, and occasionally when they find some kind of misalignment, things have changed due to buildings settling and moving and expanding, shrinking. Some adjustments can be made because of the load indicator. Insulation. Most piping is hot, higher temperature than the surrounding air. To reduce loss of heat or heat transfer from the piping, we're going to usually cover it up in insulation. If we insulate, it keeps the heat inside the piping, prevents surroundings from being heated, and if you're an operator in the plant, you'll appreciate the heat being kept inside the insulation. On the occasion that we have something in the pipe that's cold, refrigerant can be going between units and out to cooling units. We'll also insulate it to prevent condensation. Cold piping is going to be wet a lot all the time, and if we insulate it, we'll reduce the effect of corrosion. So what do we insulate piping? 16-8 starts a pretty long list of different materials. We're just going to hit the highlights. Piping insulation. High insulating value, of course, right? If we were to rate pipe insulation with R value, the higher the R value, the happier per cost of material, the happier we should be. Don't forget that insulating or insulation means we're not conducting heat. Okay, we're going to talk about that more in book 3, but insulating something or keeping the heat in is the converse is low conductivity of heat. So it doesn't let the heat from the piping get to the outside. The whole reason for having the insulation in all the places we use it. Vermin proof. Animals will and can and often do nest and eat this stuff. So better insulation will be vermin proof, non-corrosive, retains shape and insulating value when wet. Most of this piping is outside. So even though we clad it and seal it up, we want to make sure it's something that works when it's wet. So an insulation is a material that does not transmit heat well. It transmits heat poorly. Air pockets is the most efficient type. So some kind of foam or material with lots of air. So insulation is generally light stuff. So lower the K, the better the insulator. And we talk about K and heat transmittance more in book 3. All this stuff is listed in your book. We're just going to look at features of a couple of them. Okay, there's a description of all of them in the book. Feel free to read that when you're ready to fall asleep. Glass fiber is a common insulation material. It does absorb water and withstands temperatures to 454 C. There's also mineral fiber, more common now, the mineral fibers. Glass fiber has a lot of things that'll fly around and get in your lungs and cause you all kinds of grief. Almost as bad or maybe worse than the older asbestos that was used. Expanded silica. I think this is the most common one now, expanded silica, and a brand name is perlite, made from volcanic rock. These are plastic insulations. Notice it's not for high temperatures. So here's other plastics, 150 to 183, not necessarily fire retardant. If we're insulating inside of a furnace or firebox, we're going to use refractory type insulation. These will give us the high temperature ratings. These are applied in between fixed pieces of insulation. Other ones, magnesia, reflective stainless steel, spaced and baffled for fairly hot situations. And the pieces of insulation can look like this. It can be ready to go on the piping. They strap it on, they cover it up with cladding, fill in the joints and the elbows with cement and stuff. And it looks awful, can look awful pretty out there in the unit if they do a good job. How do we control expansion in piping? Two ways.
Joints and bends.
Yeah, the hangers and supports are for support, and anchoring it does not control the expansion, okay? Expansion joints or expansion bends. If we have a corrugated bellows joint, it's good to about 2000 kPa, according to the textbook. There's always newer models and different brands. To allow axial movement of piping, we use something called an adjustable roller stand. The anchor chair just simply supports it. What's in a name? Anchor. Anchor means fix it in place. Supports horizontal piping with vertical movement, something called the constant support hanger. Glass fiber insulation, good to 454. When we use low temperature insulation, it's for this, okay? Not these ones. Okay, I have a slide here. We're really not gonna, there was some code questions. Oh, under the piping support 16-6, it talks about a certain code. So I put some slides in that I later decided to remove, and I see I left them in tonight, but we'll see these again. Okay. We're really just going to need to know the name of 4 sections of ASME for the most part. 1 and 4 and 6 and 7. And then we'll know the difference between construction of different kinds of boilers, heating boiler, power boiler, construction or operation. Any questions on piping and insulation and supports and expansion joints? All good? Everybody's happy? No one fell asleep yet. A full house of students. Thank you for continuing to come back. Chapter 17, steam traps. So we're going to kind of slow down here and explain a few things. We may look at a video or two. Purpose of a steam trap. A steam trap will discharge water. In a steam system, we're going to talk about water and call it condensate. But we need to get you used to the idea that what condensate is water. We're also going to remove some air, and we'll talk about how that happens. And this whole chapter is specific to steam piping. Okay, this applies to steam in a pipe. What we need to do to prevent steam hammer. And what we need to do to prevent steam hammer is we need to discharge the water and air from any steam line, any steam equipment, and keep the steam in. So we're keeping the steam in, getting rid of the water. There's three general classes or types of traps. We're just going to look at two of them. Look at mechanical traps, kind of the old standby. More modern type of steam trap is thermostatic. And then these are really for very high pressure systems, and they're, I think when the book was written, they were limited use. They were kind of new stuff, and they were misunderstood and not being used a lot, but they've not been added into the course, so we're not going to look at them other than remember that it's not, thermodynamic is not thermostatic. This is something different. Okay. Purpose of a steam trap is to discharge or remove any condensate. We call condensate water, also air, from the steam lines. No steam shall escape. How do we do that? Mechanical class, something mechanical is reacting to liquid level. So if there's some, let's draw ourselves a steam header across the top, a big 6-inch steam line going from one end of the building to the other, steam coming in, boilers are on the left, and users are way over on the right. This could be, let's say this is a 26 meter section of pipe. And somewhere on this section of pipe, if we have a mile of piping, we're probably going to have a dozen steam traps along the pipe. So we're just going to pick a low point. In this straight run here, it's anywhere will do. The piping will be sloped or pitched according to local pipe fitting codes, but all along the line, we're going to have a bunch of these traps, and we're going to have a little connection from the bottom of our steam line. We're going to connect it to the trap. So there are going to be some things in here, but we'll talk about what they are later. There's going to be a valve for sure. There's probably going to be a strainer. And steam is going to go in here. And as this steam is going along, let's say it's 300 degrees coming out of the boiler. Even though this is a well-insulated piece of pipe, it's probably going to get a little bit cooler as it goes all the way over to the user side of the building. Okay? As the steam gets a little cooler, what's going to happen?
Condenses into water.
No, there's going to be a little bit of water. Always going to be a little bit of water. Okay? So a little bit of water will find the lowest point, and we'll go down the line into the steam trap. And at some point, this little housing, and this device, I'm going to say this device on my screen is about 6 inches tall. And the physical size of a ball trap could be about 6 inches tall. There it is, hanging on the lowest point of our steam line, which is a leg, a drain off of the line. and a little bit of water comes in, a little bit more water. Does anyone recognize what we have here?
Float valve.
It's a float. And when something is sitting in water, it's going to get, when this level of water comes higher, it's going to get pushed up. If you look closely in here, you see there's a little valve. So when the float is pushed up, because there's a bunch of water in here, it's going to open the valve, and then the water is going to go away. That's the intent of a steam trap. That's the very simplest explanation. If there's water in here, we want to get rid of it as soon as we can. So it's going to go into the trap. Trap removes the water, drains the condensate. A mechanical trap responds to the liquid level. As the liquid level comes up, a little valve opens, gets rid of the water. It's just that simple. Okay. Additionally, in here we have a air vent, and we'll look at these in more detail in other chapters. Should this housing collect some quantity of air, it will happen. This little guy opens up to let the air. Where does the air go? It goes out with the water. Okay, we're getting rid of water and air. Mechanical, this particular kind is called a ball float trap. The float floats up with a level, opens the valve, lets the water go away. Another mechanical trap is called a bucket trap, or inverted bucket in this case. So we've got something called a bucket. What color am I going to draw the bucket with? Not a bucket. Ugh. Bucket's got a little hole in it. Why do you think the bucket has a little hole in it?
Once the water level reaches up to that point, that's where it drains.
Yeah. So this will float. We're going to connect some steam to the bottom here. And as long as this thing is just full of steam, nothing will happen. It will have a closed valve. Oh, as long as this thing is full of steam, it's going to float to the top. Okay. When some water collects around the outside, it's going to collect in the bottom, the level's going to come up. And the bucket will drop, open the valve, and let the water out. Okay, this is the diagram. This is what it physically looks like when it's cut open. And notice there's a strainer on the inlet. Thermostatic trap is different than a mechanical trap. Thermostatic responds to temperature difference between the steam and the condensate. So this trap is going to be full of steam. Oops. This trap is going to be full of steam. This trap is full of steam over here on the right. The bellows is heated up. The little valve in the bottom is closed. Okay. Inlet is on the side, so the inlet is here. Everything in this one, closed valve. Steam is held in the system. As water starts to collect, level gets higher and higher, it cools the bellows. And when the bellows is hot over here, it's expanded, pushing down on the valve. As it cools, moving over this way, it's going to shrink and open the valve and let the water out. Let the water out the drain, responding to the difference in temperature. Okay, bellows is hot, it pushes down, closes the valve. Bellows cools off, it lifts up, opens the valve, dumps the water. Thermostatic type, bimetallic type is also thermostatic, responding to temperature. And there's bimetal strip in here that's holding a valve closed when the strip is hot. When this area is filled with steam, should water come in and cool things down, it will open. This bar will straighten out and open the valve and let the water out of the trap. So a couple different ways of doing things. And the other type is thermodynamic. So thermostatic and mechanical are the two that we're going to talk about. Thermodynamic works differently. So mechanical ball trap, some more details in there, things to read about. I think this is straight out of the book, isn't it? Maybe not. Out of an older book. But the description's all there in the textbook. Let's have a look at a video. Start it all by itself.
Float and thermostatic traps offer a combination of mechanical and thermostatic operation. A closed float is used to sense the density difference between a gas and a liquid. The float is attached to one end of a lever which pivots inside the trap. At the opposite end of this lever is a valve that is seated when the float is at rest. Condensate enters through the inlet near the top of the trap and raises the float, opening the valve. The condensate drains from the trap through the outlet near the bottom, leaving a condensate seal between the inlet and the valve. Above this seal, near the top of the trap, is a thermostatic bellows. The bellows responds to temperature change. When this space is filled with hot steam, the thermostatic valve is closed. Non-condensables, such as air, mix with the steam and cool the space near the top of the trap. When the bellows element cools sufficiently, the thermostatic valve will open and vent these gases into a passage leading to the trap discharge. At startup, the float is down, the float valve closed, and the thermostatic valve wide open. Non-condensable gases reaching the trap are immediately vented through the thermostatic valve at the top of the trap. Condensate collects at the bottom of the trap until the float begins to rise, opening the float valve. The float valve normally drains continuously from this point. The condensate level in the trap lowers and raises the float height, thus modulating the discharge flow. When steam reaches the trap, it collects above the condensate level and heats the thermostatic element, closing its valve. Hereafter, the thermostatic valve will open intermittently to vent mixtures of non-condensables and steam. Should the trap become waterlogged, cooled condensate would open this valve and drain to the discharge line.
Okay, and the inverted bucket works much the same. Floats up and down as the level of the water changes. And there's a video here, but we'll just skip over that one. It's identical. Thermostatic traps operates on different steppers. So the first two we saw were the ball float and the bucket float, and they react to level. They're mechanical, different than thermostatic. Thermostatic reacts to temperature. So there's a bellows here that's a sealed unit. It's full of filled with an alcohol water mixture that expands when heated. So when steam is in the trap, it holds this valve shut. When water condenses inside the trap, it shrinks the bellows and opens the valve. Thermostatic bimetallic trap. This is a video. It's the This one has bimetallic washers. This one has a bimetallic strip, so when it's heated with steam, it pushes down, closing the valve, and when it cools off, it will open and close the trap. When we install a trap, I talked about other things being in the piping, so our steam header is up here. We've got a leg off of the steam header. We've got a isolation valve, a strainer, a trap, a check valve, another isolation valve. Often you'll see them installed like this with, so here's a steam trap at the bottom of this system, another steam trap at the bottom on this side. You'll usually see them with double traps. So there's two lines here. When one trap malfunctions or wears out, needs servicing or inspecting, you can use the other trap. And condensate is piped back into our condensate system. Strainers are important. There's a video here of a type of Y strainer. This is the video of the, I just skipped over the video that we looked at the beginning. Those of you that missed it will have a double chance to see it. It's here in this slideshow, and it's also at the beginning. It's called Water Hammer. It shows a destructive force of phase changes within a pipeline. Water hammer can simply be caused by closing a valve too fast with a liquid flow. Steam hammer is a more severe situation of the same phenomena. The bubbles, a lot of water can be collecting in a steam header if there's a trap that's malfunctioning or left blocked in. There's not enough traps in your system. Steam bubbles, water can fill up the steam line enough to trap some bubbles, and then when those bubbles collapse, there's forces, great forces when those bubbles collapse as they condense. So let's have a look at, I think this is also a water hammer video. Let's have a look.
Geerstra, an international manufacturer of valves and control technology, commissioned the world's first complete glass steam system in 2009. For the first time ever, it's now possible to look right into a steam generator and see how steam bubbles arise, how feed water is deaerated, and how the various types of steam traps really work. A number of videos take a look at important facets of the steam condensate system and its operation. Thermodynamic processes taking place in the generation of steam, as well as during condensation, condensate discharge, and the origination of the water hammer effect are shown in a way that's easy to understand. This video looks at condensate discharge using various kinds of steam traps, as demonstrated in the glass steam system of Geerstra AG, Bremen. The steam system consists of a secondary steam generator with a service pressure of 1.3 bar G, corresponding to a saturation temperature of 124.7 degrees centigrade. The capacity of the steam boiler is 50 kilowatts, which yields a steam flow rate of 80 kilograms per hour. As the condenser, we are using a glass heat exchanger mounted above the steam generator. Cooling water flows in the tubes, while steam flows in the jacket around the tubes. After passing through the steam traps, the condensate is collected in a glass condensate tank at normal atmospheric pressure. In this film clip, the origin and effect of thermal pressure pulses, generally known as water hammer, will be demonstrated. For this, steam is introduced into a horizontal glass tube with a slight upward inclination, thus forming a pocket of water. The water enclosed in the tube on the left-hand side is cold, whereas steam is available on the right-hand side. This represents a typical startup situation for pipe segments with poor drainage. The steam valve is now opened slowly. First of all, 1 or 2 air bubbles flow to the left. After a short while, the water has been warmed up slightly. Now the first steam bubbles are seen flowing through the water. These bubbles release their heat suddenly and condense into water. The water attempts to fill this vacuum as quickly as possible, collapsing into the empty space. The water quantities accelerated in this way must now be stopped in fractions of a second. It's possible for pressure shocks with peak values of more than 1,000 bar to be created. This becomes noticeable through the visible shocks and explosive sounds. The shutoff valve must be opened very slowly to ensure that the number of steam bubbles passing into the water is kept as low as possible. Once the entire body of water has warmed up to boiling point, the steam bubbles condense at only a very slow rate. There is then no longer any danger of water hammer. The experiment is repeated a second time. This time, however, this part of the horizontal tube is arranged to have a slight drop towards a siphon. Having the siphon downstream ensures that there is always a steam bubble in the horizontal part, and the water flows along the bottom. Through their volume, the steam bubbles at the top of the tube form a buffer space, which minimizes the water hammer at startup and allows the startup process to be initiated faster and with less risk. Once again, the valve is first opened slowly. After the water has warmed up a little, it can be seen that a vapor phase is created at the top of the tube. Now the valve can be opened more quickly. The strength of the water hammer is much lower than in the previous experiment. For this reason, Geistra recommends the use of the condensate dampening pot type ED for condensate lines where the pipework changes from the horizontal to the vertical orientation. Thank you for watching.
Not quite as exciting as he tried to let on, but interesting that you can see the phenomenon. Literally, if he'd cranked that steam valve open with glass piping, they would have smashed it to bits. Those of you that saw the first water hammer video we showed just a few minutes before 6, they talked about 50 G and 3.5 tons on a small little 2-inch valve disc. So tremendous forces can be caused by not removing condensate from steam lines. Okay, so remember, a steam trap will help you out. It will automatically remove condensate, also air, and not allow the steam to pass. So it keeps the steam in the system, gets rid of the water. This is not the right answer. We're not removing the steam and keeping the water in. It's the other way around. Mechanical steam trap uses what? Keyword mechanical. Responds to liquid level in the trap. Okay. Not difference in pressure. This is mechanical, difference in temperature, and not difference in specific gravity. Dissimilar metals bend or deflect in the thermostatic trap. Where do we install steam traps? At the lowest point in the system. Remember to install steam traps at the lowest point. Other things go at the highest point. If you have a system that has air collecting, we're going to have air vents at the higher points. Something ahead of steam traps, these mechanical traps have little passages and small valves. We're going to put strainers in. Okay. A check valve, yes, but not ahead. It will, yeah, strainer ahead, check valve after. So improper drainage of steam lines may cause water and steam or steam hammer. So you need to make sure a system is as water-free as possible. Ensure no water or condensate is in the piping. Okay. So you won't be closing the drains. You'll start with them open You will not be too worried about that. You won't have all the valves closed. And check valves, you don't have a choice of opening and closing through whatever means possible. And it's the setup of the traps. There's always going to be a bypass and a drain or a way to start getting rid of the water. What is water hammer? It is a series of shocks caused by a sudden change in the velocity of the water. Okay? Water hammer. Close the valve too hard, you're going to cause that shock wave going back. And the first shock wave going back is minor. When that shock wave goes back, it'll cause the voids in the fluid. And then the reverse flow slamming back against the valve is where the tremendous forces are created. Remember, a mechanical ball trap or a bucket trap responds to liquid level. These are mechanical traps. Get rid of the water and keep the steam in. Okay. Bimetal trap actuates based on temperature. Okay. Not density, not velocity, not specific gravity, but temperature. Install a strainer ahead of the trap to prevent foreign matter. Right? Steam trap will discharge water and condensate from the steam lines or other equipment without letting steam escape. Okay. Any questions on traps? Okay, good to go. We'll keep going forward and introduce you to valves. So I played a couple videos tonight. Did anybody experience getting kicked out? You did. Okay, if I play another video, so you got kicked out, you got back in, no problem?
No, it took me a few times to get back in this time. Usually I just go through the system and back in, but this time it got to as far as letting me back into Teams and took a while.
If you're having that issue, is anyone else having it?
Me too. Me too. Same.
Ray and Peter?
Yeah. I normally get kicked at the same time, just before 8 o'clock.
Weird.
Yeah.
I still recommend a hardwire for your internet connection. I think that will help. But you know, if you miss the video or you just see part of it, it's there for you to look at in the slideshow, right?
Yeah.
A little bit about valves. Yeah, I really like to show some of these valve videos. So here we go. Let's just look at a couple instead of a whole bunch, and then you guys can, if you can get back in, that's good. Our number is down 1, but sometimes people leave early.
Many process systems have to be supplied with a...
Is this big enough for most people, or you prefer I can do it this way, and I think
Bigger, please.
Bigger is better.
with a variety of fluids in order to operate properly. And a maze of piping systems carries these fluids throughout the plant. The flow of fluids through piping systems is controlled by valves. In order to keep fluids flowing smoothly, operators need to know how valves operate and how to keep them working properly. Valves are used to control the flow of liquids or gases in a plant. When a valve is opened, flow begins. When a valve is closed, flow is stopped. Many valves operate in either the fully open or fully closed position. These kinds of valves may be referred to as on-off valves. Other valves regulate or throttle fluid flow. This can be done by partially opening or closing a valve. Valves that operate in this way are called throttling valves. Some valves may allow fluid flow in only one direction. These valves are called one-way valves or check valves. Still other valves are used to relieve excess pressure from a process system to protect equipment and personnel. These valves are called relief valves or safety valves. Regardless of the types of valves in a process system, all of them must be correctly positioned for the system to operate properly. Positioning valves so that the ones that should be open are open and the ones that should be closed are closed is called lining up the valves. Your plant procedures probably contain routine valve lineups. They may also include checklists to show what the proper positions of the valve should be for particular process operations, as well as piping system diagrams, which can be used to help determine valve locations and positions. When performing a valve lineup, an operator would use checklists and piping system diagrams to verify valve identifications and positions. Valves are usually labeled with ID numbers that are also shown on checklists and diagrams. By cross-checking the number on the valve label with the number on the checklist and the piping system diagram, an operator can make sure that he's at the right valve. The operator can then position that valve as specified in the checklist. These steps should be repeated for all the valves on the checklist until the valve lineup is complete. Even though valves may look different, many types of valves have the same basic parts. Being able to operate valves properly and identify problems that may occur requires an understanding of valve construction. The main part of most valves is the valve body. This is the part of the valve through which the fluid passes. The valve body also contains some of the other valve parts and provides the means to connect the valve to other components. The method used to connect a valve in a piping system depends on system characteristics such as the amount of pressure that the connection must contain. There are essentially three main methods of attaching valves in piping systems. The connection may be welded, threaded, or flanged. Welded connections are used in steam lines or high-pressure process piping where other means of attachment may be more likely to leak. Threaded connections are generally used on small valves in low-pressure systems. And flanged connections are commonly used where operating conditions may require frequent valve replacement or repair. Other parts of a valve may include a seating area or seat, a disc, a bonnet, packing material, a packing gland, and a stem with a hand wheel attached to it. The seating area or seat is a stationary part of a valve. It's used with the disc, which is a movable part, to control flow through the valve. As the disc moves toward the seat, flow through the valve is reduced. And when the disc presses against the seat, flow through the valve is stopped. As the disc moves away from the seat, flow through the valve is increased until the disc reaches its limit of travel. At this point, the valve is fully open and maximum flow is passing through the valve. When a valve is partially open, the valve is said to be in a throttled position. The disc is attached to the stem, which in turn is attached to the hand wheel. As the hand wheel is turned, the stem moves. This repositions the disc with regard to the seat and changes the flow through the valve. The valve bonnet seals the top of the valve body. The stem extends through the bonnet and into a space called a stuffing box. The stuffing box holds the packing, which is installed around the stem. The packing is flexible and leak resistant. It prevents leakage from the valve along the stem. The pressure applied to the packing by the packing gland is adjusted using gland nuts. The pressure is adjusted so that the valve stem can be moved as the valve is repositioned, but leakage does not occur around the stem. Valves, like many other components, require some routine maintenance and are susceptible to mechanical problems. In this part of the program, we're going to take a look at one type of valve problem, a leak. Then we'll look at a routine maintenance task that an operator may have to perform to keep valves operating properly. If a valve's packing becomes worn or fails completely, fluid will leak out around the stem. This type of leak is commonly referred to as a packing leak. In most valves, the packing can be adjusted to stop minor packing leaks. Packing is adjusted by alternately tightening the packing gland nuts, usually a quarter turn each at a time. This ensures that the packing gland doesn't become cocked in the stuffing box as the gland nuts are tightened. The packing is not the only place where a valve may leak. Another place is the joint where the bonnet of the valve attaches to the body. A leak in this area is commonly referred to as a body-to-bonnet leak. Still another place that valves can leak is where the body of the valve attaches to the piping system. On valve bodies with flanges, this leak is commonly called a flange leak. On valves that are attached to piping using methods other than flanged connections, this leak may simply be called a connection leak. The final leak that we're going to look at, and one that is not so obvious, is an internal leak through a valve. As a valve disc and seat wear, fluid may begin to leak by the seat when the valve is fully closed. When this happens, the valve is said to be leaking through. This leak can be detected only by carefully observing plant instrumentation or conditions on both sides of the valve. Besides locating and identifying leaks, another task that an operator may have to perform is valve lubrication. Valves need lubrication to prevent components from wearing during operation. Each type of valve may require a different type of lubricant or method to apply the lubricant. For example, some valves have grease fittings and require the use of a grease gun to lubricate them, while other valves may have the lubricant applied directly to a component, such as this valve stem. Because there's so many different methods that may be used to apply lubricant, you should always check your company's procedures before lubricating a valve. In this topic, we've seen how valves are used to control the flow of fluids, and we've identified some basic valve components. We also saw some methods used to attach valves to process piping, as well as some maintenance tasks an operator may have to perform. Now, try some practice questions. Many valves operate in either the fully open or fully closed position. These kinds of valves may be referred to as on-off valves. Other valves regulate or throttle fluid flow. This can be done by partially opening or closing a valve. Valves that operate in this way are called throttling valves. Some valves may allow fluid flow in only one direction. These valves are called one-way valves or check valves. Still other valves are used to relieve excess pressure from a process system to protect equipment and personnel. These valves are called relief valves or safety valves. Other parts of a valve may include a seating area or seat, a disc, a bonnet, packing material, a packing gland, and a stem with a hand wheel attached to it. If a valve's packing becomes worn or fails completely, fluid will leak out around the stem. This type of leak is commonly referred to as a packing leak. In most valves, the packing can be adjusted to stop minor packing leaks. Packing is adjusted by alternately tightening the packing gland nuts, usually a quarter turn each at a time. This ensures that the packing gland doesn't become cocked in the stuffing box as the gland nuts are tightened.
Hey, anybody get kicked out? Everybody's good? Let's look at this one. That was a good one. I realized for those of you that work with this stuff every day, it's pretty boring, but you know what? I think I counted 15 possible exam question answers, word for word, right out of that video. So you might want to look at it again when you get a chance.
A variety of fluids in order to operate properly. And a maze of piping systems carries these fluids throughout the plant.
This is the same one.
The flow of fluids through piping systems is controlled by valves. In order to keep fluids flowing smoothly, operators need to know how valves operate and how.
Sorry, that was the same one. Let's try this one.
One type of valve that's commonly used in process systems to start and stop flow is the gate valve. Gate valves are designed to be used primarily for on-off purposes. They operate best in either the fully open or fully closed position. Gate valves are often used to isolate equipment. For example, these gate valves are in the suction and discharge lines of a pump. Shutting the valves isolates the pump from the rest of the system. Gate valves are also used in situations where the valve position seldom changes, such as a drain valve on a tank. In a situation like this, the valve would be closed most of the time. Gate valves are pretty easy to identify because they have relatively long bodies and long valve stems. On a piping system diagram, a gate valve is usually represented by this symbol. If the symbol looks like this, it means the valve is normally open in the system. If a symbol is filled in, it means the valve is normally closed. Other types of notation may also be used to show valve positions, such as the letters NC for normally closed and NO for normally open. Now that we've seen the symbols for a gate valve, let's look at the valve's parts. A gate valve consists of a valve body, a seating area or seat, a disc, a bonnet, a stem with a hand wheel attached to it, a stuffing box, packing, and a packing gland with gland nuts. The disc is usually wedge-shaped and fits snugly in the seat when the valve is closed. When the disc is completely raised, flow is straight through the valve with very little obstruction. The stuffing box holds the packing in place, and the packing gland fits into the top of the stuffing box. The gland nuts are used to tighten down on the packing gland. As I said, gate valves are normally used in on-off applications, but in an emergency, they can be used to throttle flow. However, long-term use as a throttling valve can damage a gate valve. In many types of gate valves, when the disc is raised slightly, fluid flow through the valve creates turbulence, which causes the disc to swing from side to side, banging or chattering against the seat of the valve. This chattering will cause wear on the seat and disc, and eventually, the valve will not shut off flow when it's completely closed. One type of valve that's commonly used in process systems is the globe valve. A globe valve can be used as an on-off valve to isolate components and as a throttling valve to regulate the flow of fluid to components. Let's examine the construction of a globe valve to see how this is possible. A globe valve consists of a globe-shaped valve body, a seating area or seat, a bonnet, a disc, a stem with a hand wheel attached to it, a stuffing box, packing, and a packing gland with a gland nut. Fluid flow enters a globe valve here and exits here, making several right-angled turns as it passes through the valve. Globe valves are normally arranged in a piping system so that the higher pressure side of the piping system is acting under the disc of the valve. This makes it easier for an operator to open the valve. As you can see, as a globe valve is opened, the entire disc and seat are exposed to the fluid flow. This design feature prevents uneven wear of the seat and disc. In addition to the regular seat, some globe valves, like some other types of valves, have a back seat. If we look inside the bonnet of a globe valve that has a back seat, we can see that when the valve is fully open, the top side of the disc seats against the back seat. This prevents the packing of the valve from being constantly exposed to piping system pressure and reduces the likelihood of a packing leak. You can usually recognize a globe valve by its globe-shaped body. However, not all globe valves look like this one. Here is another type of globe valve called an angle valve. It's easy to spot because of its globe-shaped body with piping connections at a right angle. Angle valves are used to change the direction of fluid flow. This is another type of globe valve called a needle valve. Needle valves are usually smaller than other globe valves and are designed to give fine control of flow in small diameter piping. A needle valve has basically the same parts as other globe valves, but its disc is shaped differently, like a needle. The needle extends deep into the seating area of the valve. A small movement of the stem causes a small, gradual change in the flow rate through the valve. This gives the needle valve an extremely fine throttling ability. On a piping system diagram, a needle valve generally looks like this. An angle valve generally looks like this, And a globe valve generally looks like this. If the symbols look like this or have the letters NO beside them, the valves are normally open. If the symbols are filled in or have the letters NC beside them, the valves are normally closed. The symbol may also be shown partially filled in. When the symbol is shown this way, the valve is in a throttled position. Plug valves are generally used for on-off purposes in situations that require quick valve operation and a tight shutoff, such as in this gas line. Plug valves can usually be recognized by their cylindrically shaped midsection and flat bottom. On a piping diagram, the symbol for a plug valve generally looks like this. If the symbol looks like this or has the letters NO beside it, then the plug valve is normally open. If the symbol is filled in or has the letters NC beside it, then the valve is normally closed. A plug valve consists of a valve body, a seating area or seat, a stem with a handle attached to it, packing, and a packing gland with packing gland bolts. Instead of a disc, a plug valve has a plug to control flow through it. The plug has an opening straight through it, and it rotates inside the valve body. The plug's position is adjusted by turning the handle. When the opening in the plug is in line with the valve's inlet and outlet, the valve is fully open. To close the valve, the plug is turned so that the opening is perpendicular to the valve's inlet and outlet. So a plug valve can go from fully open to fully closed with only a 90-degree or 1/4 turn of the handle. Also, the handle on a plug valve is usually aligned with the opening through the plug, so that the handle position indicates the valve position. If the handle of the valve is in line with the piping, then the valve is open. If the handle of the valve is perpendicular to the piping, then the valve is closed. For complete shutoff of fluid flow, the plug and seat must make a close fit as the plug turns in the valve body. The close fit is needed to avoid leakage around the plug. But because of this close fit, turning the plug can gradually wear out the plug and seat. If either one wears out, fluid flow won't be shut off completely when the valve is closed. To minimize the friction between the plug and the seat, many plug valves are lubricated. Some plug valves are equipped with a fitting on top of the stem through which lubricant is supplied to the plug. Now let's take a look at another type of plug valve, the multi-port plug valve. Ball valves are commonly used for on-off purposes requiring fast valve positioning in process systems. A ball valve consists of a valve body, a stem with a handle attached to it, a ball with an opening straight through it, a seal around the stem that prevents leakage along the stem, and two-part ring-shaped seats, which are commonly called wipers. A ball valve can be opened or closed by turning the handle 1/4 turn. The handle is usually aligned with the opening in the ball, so that valve position can be determined by the handle position. The body of a ball valve may be either cylindrical or round in shape. On a piping system diagram, a ball valve symbol generally looks like this. If the symbol looks like this or has the letters NO beside it, then the valve is normally open in the piping system. If the symbol is filled in or has the letters NC beside it, then the valve is normally closed. Butterfly valves are used for a variety of purposes in industrial plants. Typically, butterfly valves have round, relatively thin valve bodies. Because of this, they take up a lot less space in piping than many other types of valves. A butterfly valve consists of a valve body, a seating area or seat, a disc, a stem with a handle attached to it, a stuffing box, packing, and a packing gland with gland nuts. The disc of the butterfly valve is just slightly smaller in diameter than the inside of the piping in which the valve is installed. The disc is also relatively thin and offers little obstruction to flow when the valve is fully open. The disc is attached to the stem. The stem is used to rotate the disc when the handle is moved. The flow rate through the valve is adjusted by changing the angle of the disc. The symbol has the letters NC beside it, then the valve is normally closed. In this topic, we looked at how gate, globe, plug, ball, and butterfly valves are constructed and at how these valves operate. We also saw how you can identify these valves in piping systems and on system diagrams. Now let's try some practice questions. You can usually recognize a type of valve that's commonly used in process systems. However, not all globe valves look like this one. Here's another type of globe valve called an angle valve. It's easy to spot because of its globe-shaped body with piping connections at a right angle. Angle valves are used to change the direction of fluid flow. Gate valves are pretty easy to identify because they have relatively long bodies.
Hey, that one was hard to stop. So, there is 4 or 5 slides in a row that are videos. We saw one, and then we saw the second one. And then so this one, we saw this one. Okay, there's one more, and this is a good one too. I'm not going to bore you to tears with it, but I mentioned the first video, slide number 347, had a number of potential Thursday night jackpots, potential exam answers. And I made a list on this one we just watched, 13 minutes long. Gate valves 5, globe valves 4, needle valves 3, plug valves 6, ball valves 4, and butterfly 4. So worthwhile to note the conversations in those videos. So we'll just review the types, and then we'll be able to wrap up chapter 18. And I really like the language. Those are sort of old school videos, but the language follows what the language you're going to use in the conversation about valve types. Gate valves. So the valve type that look like this, the tall body and the long stem, it's called a gate valve. Described very well in the video. Also talked about it being usually fully closed or fully open, not that suitable for throttling. He did talk about it could be in an emergency, but not designed for it. One of the reasons is the design will wear and erode if the gate is not completely out of the flow. So gate valves normally fully open, fully closed. So because of that, they are suitable as a stop or isolating valve. Conditions require fully open or fully closed, no flow. When this type of valve is completely open, there's a full pipe. There's nothing in the flow for restriction, so minimal restriction. Has less restriction than a globe valve, is normally fully open or fully closed, and the applications are different than the globe valve. So this here is just a reminder, not suitable for throttling. Best as stop or isolating. Video, he called them on-off valves, so full flow or no flow. And resistance to flow is minimal. And there's a picture of the gate closing the valve and showing resistance to flow if it's partially open. Okay. Another shot of a gate valve with all the parts shown there. Picture out of the book is this one, showing all the parts that were described in great detail. Remember, a globe valve is different than a gate valve. So we have a body, we have a bonnet, some kind of a seal or packing with a packing nut or packing bolts, a stem and a handle like all the other valve types. But the disc is sitting across the flow, so flow must change direction. And there is resistance to flow, but because of this design, the flow is slowed down when it changes direction. It allows us to throttle the flow and not wear out or damage the disc. Okay, so this is a globe valve. It has that round shaped body as opposed to that tall body and bonnet with the long stem. Due to the construction, the globe valve is ideal for throttling or regulating the flow. There will be minimum damage. The damage to the seat would be called wire drawing or seat erosion. Okay. But when we change directions, flow has to change direction. We have some resistance to flow. This opening is very small compared to the diameter of the piping. So there's a restriction or pressure drop across the valve. Globe valve offers more resistance to flow than the gate valve. But a globe valve is ideal for throttling or regulating the flow because that flow past the disc is spread around the disc. It doesn't damage the disc as we throttle or control the flow. So there's the globe valve with all the parts. Needle valve is simply a variation on a globe valve. It'll have a skinny or narrow seat and fine threads on the stem so that we can make small adjustments for very precise flow control. Often a normal application would be something like a continuous blow off or blow down where we're blowing down from the surface of a boiler, continuous but small amounts, and also for chemical feed control. A butterfly valve. So these guys have a flat disc that's in the body of the valve. The valve is body of the valve is a thin structure, and one feature of a butterfly valve is this lever for a handle. And because this disc turns across the flow for shutoff and along with the flow for being wide open, it's called 90-degree operation. I'll remind you to remember that 90 degrees is a quarter turn. These are quarter turn valves. Exam question might say half turn, and most people pick half turn. Okay, ball valves and butterfly valves, quarter turn operation. These guys are also, butterfly valves also lightweight, easy to operate because of the 90-degree operation. Self-cleaning, there's not a lot of resistance to flow. So that means negligible pressure drop across the valve when fully open. And I've seen them used for throttling and in some cases, not the best for this type of valve, but can be used for throttling. Ball valves are kind of universal. We can use them for isolation and we can use them for throttling. They work quite well. They have a round or spherical plug inside the body. So it's called a ball valve, something round inside here. It's got a hole drilled through it. When we turn it, the handle along the pipe, the valve is open. When we turn the 90-degree quarter turn handle across the pipe, the valve is closed. Spherical or round plug inside the body. Plug is bored to allow for full flow. When turned parallel, it's wide open. We can see that here. Quarter turn from fully open to fully closed, and the lever handle serves as open or shut. So this one here shows the valve is closed and the handle is perpendicular to the pipe. Spherical plug allows precise control of flow through the valve. Tight shutoff when used in the closed position. And torque is negligible. So this is an easy valve to operate. There's a nice cutaway shot of a ball valve. Plug valves were shown in the video, page 18. It's kind of a variation on the theme of a ball valve. It has a tapered or barrel-shaped plug inside the body, and has an opening through the plug. And when the plug is turned crossways in the line, it's also 90-degree open to close, quarter turn. And when this plug is turned to allow flow to come through, it's a fairly low restriction of flow. Plug valve is also a quarter turn valve. Plug has a tapered or straight cylinder shaped for allowing flow through a passage. Inserted into the cavity of the valve body, the hole in the plug lines up with the axis and the opening when it's wide open. These can have periodic lubrication attachments. So this has, in this drawing, an attachment on the stem or the shaft to allow lubrication to prevent jamming. Grease is injected at the top of the stem and distributed down through these surfaces on the side of the plug. Pressure drop across a plug valve is also very low and considered to be self-cleaning, used as quick opening valves for gas supply lines. Low pressure steam lines, fairly popular in water treatment and chemical industry. So the big feature of this one is grease injection to lubricate that plug. Check valves, a couple kinds of check valves, a swing check valve and a lift check valve. Check valve purpose is to prevent reversal of flow. Swing check valve has a straight line flow, offers little resistance to flow, has a disc hinged at the top, swinging freely inside the pipe. So this is a pivot, disc hanging on a pivot. Flow is coming into this valve. It will push the disc open and flow will carry on. Should flow try to come back, it pushes the disc shut, swings over in a swing check valve. Lift check is made a little differently. We have a picture here. Has something called a dash pot to cushion the action of a disc. If a check valve is very big, 6 inches and up, I'm gonna guess. Low reversal of flow could happen in a hurry. And if this is a big heavy object in a line, it can slam shut and even break the flapper. So they can be constructed with something to, this one has a spring and something called a dash pot that cushions that action. Should this reversal of flow being happen a lot in a check valve, you're going to hear those swing type hammering and chattering and rattling, and then they put in a lift check to cushion that action. Non-return stop valve. So on top of most boilers, you're going to see something that is a combination check valve and manual valve with a hand wheel and a stem and a disc and a seat. Before starting up a boiler, this valve would be, hand wheel would be cranked down, this valve would be shut. Once we've got a boiler commissioned and steam flowing, this hand wheel would be backed off. And when boiler pressure becomes higher than header pressure, than outlet pressure, this disc would freely move up and the valve would remain wide open. Should something happen in the system, boiler shuts down, this disc is free to close. If pressure tries to come back from the header, it will close the disc and prevent backflow into the boiler. So we call it a non-return valve. Non-return boiler stop valve. Designed for one-way flow only. Should a boiler tube rupture or a pressure drop from other means, the NRV or non-return stop valve will automatically close, prevent steam from other boilers or the header from entering the damaged boiler. And once that valve closes, you can wind the hand lever down to hold the disc shut. Okay. Non-returned stop valve, stop and check. Sometimes we call it stop and check. NRV is the most non-return or non-return stop valve. This is the most common name for that device. It has a device that prevents reversal of flow through the pipe. If the valve is open, check valve will prevent a reverse flow steam into the boiler from the common main. And that's all described on page 18. So there's some variations on it. They can be this kind, sitting right on top of the boiler, or this kind in the piping. Angle type piping comes out of the boiler. There is a video in the next slide about one of these, taking it apart and doing maintenance. We're not gonna look at that, but you feel free to have a look at it. I'm gonna try and skip over it. Okay, pressure reducing valve. So a specialty type valve, page 1812, pressure reducing valve. Pressure of utilities such as city water, natural gas, compressed air might be higher than we need, more than the service pressure. For our equipment, pressure reducing valves are used to lower the supply pressure and maintain it at the required pressures. This specific type of valve for controlling pressure from a header or a main to our supply to the specific uses that we need. Adjustment is done with a stem or it'll have a stem often without a handle on it, and the adjustment will be done with a wrench or a certain kind of wrench. If we tighten the stream spring pressure, first day with my new mouth, we increase the pressure outlet. So it's adjustable. Should incoming pressure be variable, we can make adjustments. Some are automatically adjustable. How do we install them? All reducing valves should be installed with isolating valves. So there'd be a couple of gate valves on either side, a bypass valve. Bypass valve would be a globe type valve or a ball valve for throttling or adjusting flow. Should this thing be out of service for maintenance, we can make adjustments and continue to run our equipment. Should also have a pressure gauge and a safety valve on the pressure side of the reducing valve. So here we have our pressure reducing valve. This one has a strainer or check valve, also a bypass, should we need to remove this device for maintenance. So pressure reducing valve should have isolation valve on either side, bypass valve, downstream safety, and relief and pressure gauge. So this one shows all those devices. Bypass. Pressure reducing valve is here. This has a steam trap, so this is a steam pressure device of a pressure gauge. Sensing line over to the, so this would be one that's automatically adjustable. Valves and fittings. We talked about this with fittings, and we're going to talk about this with valves. Valves are certainly fittings, and valves are regulated by the rules and regulations, so they must also be legibly identified as to the material of construction. So there's going to be a list of 3 things: material of constructions, service conditions, and the third thing, or the first thing on the list, manufacturer's name or trademark. Service designation means what pressure, what temperature is it designed or rated for. And material designation means it's made of steel, or it's made of cast iron, or it's made of 104 stainless steel, or some number that indicates the material that it's made out of. Any questions on this one? Okay. Valve leaks. So a little bit on valve maintenance. Inspect valves frequently. He touched on this in the video, and I made a number of check marks beside each of the points. Inspect valves frequently. Repair leaks immediately. A leak in a valve can often be an easy fix. Small leaks left to neglect or ignoring them results in damage. Different things can be damaged, and replacing a valve is always more expensive than minor repairs. Most valve stem leaks are just simply tighten the packing. Okay, it's misadjusted. Things are getting loose, tighten it up, away you go. Minor leaks can be fixed by tightening the packing. Always tighten evenly and slowly. He talked about a quarter turn at a time, generally a quarter turn on one side, quarter turn the other side. Just leave it sit for a while. You'll probably see the leak slow down, unless it's gushing. If it's gushing, you probably have a bigger problem. Lubrication of the stem. They showed bigger valves with a grease gun connection, and they showed painting the never sees or something like that on the stem, and that's has the same purpose. A few drops of oil. I've never seen oil used on a valve stem, but some kind of lubrication wiped onto the stem each time you open and close it keeps it operating smoothly and prevents any seizing up and getting out the big snipe to open the valve and possibly break the handle or your friend's arm. But according to textbook, a few drops of oil on the valve stem will reduce friction, extend the life of the packing. Okay, 397, that's the table. Chapter 18. Anyone catch the typo? I just left this word in here. Internally inspection, you can't inspect it internally without shutting the system down, but you don't necessarily have to remove the body. You can take the bonnet off and see and remove all the inside parts, such as the disc and the seat. So if you keep the disc and the seat in good shape, you're not going to have one thing in the video. He talked about internal leaking, or he called it passing through. No, he did not call it passing. He called it, anyone remember what he called it? He was talking about passing. If we have an internal leak in a valve across the disc or through the seat, then the name for that is passing. If the valve disc or the seat is damaged, the seating surfaces should be refaced. So that's the disc and the seat. And back in the day, we repaired valves and repaired valves and repaired them again. We didn't just take them out and throw them away or send them away. Some very interesting process. A new seat and a new disc. We would actually do polishing of the seat and disc for very tight closure of the valve. So kind of a science. A little review of valves. 3 things about a gate valve.
Fully open or fully closed.
Correct. Less or more restriction? Less. Same application as a glow valve? No, has different application. Not for throttling, even if it's gas, okay? So should be fully open or closed, less restriction, different applications. Glow valve. One of these is true. 2 of these are true. Glow valve is for throttling flow, and glow valves have different applications than gate valves. What is a needle valve? Oh, sorry. A valve needing lubrication. Tapered plug valve. Valve type with a dash pot. Which one?
Check.
Lift check, not the swing check. Swing is flopping around in there, and lift check has a dash pump. Lift check. Pressure regulating reducing valve. One of these is true. All right. Pressure regulating or reducing valve need all these things: safety, a bypass, and a pressure gauge. Markings on pipes and fittings. All fittings, valves are not clearly marked or rejected. Wrong material is a frequent cause of accidents. If it's correctly labeled, it should show the name or trademark. It should show the materials of construction and should show service designation, which means pressure, temperature. If not clearly identified, you're going to throw it away. Okay, send it back. What is material designation? It's just what is the material? What is it made of? Service designation, temperature, pressure rating. Okay. Leaks from valve stems normally are easily repaired by slightly tightening the gland or the packing nut. Okay, just a couple of slides. Plug valve applications, water treatment, pulp and paper, chemical, and gas isolation valves. Butterfly valves, how many degrees?
Okay, quarter turn.
90 degrees. And a ball valve is the same thing, but that's also 1/4 turn. Okay. Any questions on 18? So Garrett posted a video. Can you tell us what it is?
Oh, it was just something silly. I don't know if any of you were
It's silly,
paying
it's
attention.
funny. Okay, you
It's
guys,
hilarious.
you guys can look at
It's
it
just
in
part of
the,
this.
it's okay. You can have a look in the chat. We won't necessarily show it in the class. I may look at it later and bring it back if I get a kick out of it. I get a kick out of funny. Thermoil systems, hot oil systems, typical areas of responsibility for power engineers. And these are hot and dangerous systems. So hot things get under our control, and we'll describe them and look at some problems with them, and then that'll be the end of our night. What is a hot oil system? Hot oil is used as a thermal fluid in the place in place of steam or hot water. So instead of having steam or hot water to send heat out from a central heat port source to other vessels or heating coils, we're going to use hot oil. We'll heat it up with a furnace as a burner and coils to heat the oil, piping to distribute and return the oil, heat exchangers to transfer to the oil, and pumps to send the oil out there and bring it back. Hot oil systems use something called firing rate control to sense the outlet oil temperature. The furnace itself in a hot oil system has registers on each burner and a stack damper for controlling combustion airflow. And we have a couple of diagrams. The one that shows where the burners are is 19-6, but the one that shows the combustion control and the stack damper is 19-4. I believe that's this one. Yeah, so we show here a stack damper. The diagram just says burners at the bottom. It doesn't say how many burners. Generally, this guy's going to have multiple burners, 4, 6, 8, 10. I've operated furnaces like this with 400 burners. Each burner throat was big enough for me to put my head through. So burner about this big. This furnace with 400 burners used, at the time we talked about the amount of natural gas it was using. 2 6-inch natural gas headers at 700 psi, supplying gas. Probably used as much gas per hour as a small city such as Grand Prairie to heat all the houses and all the buildings. So this is a big furnace. Okay. This one here is a hot oil system. This is not a big furnace. That one was 12 stories high, 400 burners. This one might have one burner, possibly a couple more. Okay. Types of coils or heating coils talked about on 19.5. Combination radiant and convection heaters. I'm going to refer you to this picture. This should be bigger. But the one in the book shows the convection tubes up here in this area, in the top or the breeching. And it shows the radiant tubes within the furnace. So within the furnace, we have flames. It shows updraft burners. So we have burners in the floor, flames are shooting up. When the tubes are around the flame in a boiler or furnace like this, it's called radiant tubes. heat will go through into an upper breaching area. And tubes up in this section are getting heat from convection. They're taking more heat out of the gases as the gases pass through into the stack. So we call that convection tubes. Trying to go backwards here. So the combination of radiant heaters around the burners are only 40 to 50% efficient. So we add another oil pass or coil called the convection heaters to increase the efficiency. More heat transfer, efficiency is greater. So this combination of radiant and convection is designed for greater efficiency. Okay, radiant and convection, hot oil enters the convection section first and then flows down through the radiant tubes, goes out to the user. The gas burners are here in the floor of the furnace. Walls are brick or refractory. Something important about might have hot oil, burning fire, leaking stuff. We're going to have a concrete dike around this. In case there's any leakage, the fire is going to be concentrated. We don't want hot oil flowing out across the ground all over everywhere. So because these guys are prone to fires and leaks and problems, we have protective devices. Certainly we have interlocks and protective devices on most of the equipment we operate, but the ones that are specific here. Surge tank low oil level. So if you go back and look at the diagram here, you'll see there's a surge tank. So we're heating oil and it's going from the tubes in the furnace into a surge tank and supplied to users, exchangers for heating, and then returned to the furnace. If there's a safety valve on this system, it's going to go back into the surge tank. Flame failure systems, so flame detection on all furnaces. Low hot oil flow installed in the outlet line. Hot oil high temperature is a shutdown, also taking the temperature of the oil on the outlet line. We would be monitoring for high stack temperature. If there is a tube leak, oil spilling inside the furnace, it's going to be an instant fire. So high stack temperature is monitored. This equipment and many other equipments have what I call the big red button. ESD, emergency shutdown. Literally a big red button. If you see this thing burning up, you're going to shut it down, right? And high or low fuel gas pressure, as on any furnace, we're going to monitor, and that will be one of the protective devices. What kind of fluids do we use? Petroleum oils. They're good up to very high temperatures, but this oil will deteriorate if we exceed this. We run them too hard, run them too hot, and the molecules of the oil will actually crack or modify and create some byproducts called polymers, and they can look like this. And we start to plug up the tubes. We're going to have less heat transfer. We're going to have hot spots. We're going to have all kinds of problems. Okay, so this leads to coking and overheating of the tubes. A tube rupture and fire could literally destroy this kind of equipment. So important to inspect them annually. One of the things that's done to check for this is X-ray the tubes, radiographic inspection, used to confirm the presence of coke deposits. Because we don't want to burn it down. Health and safety, if we do get a fire, these kind of units will have dedicated fire extinguishers and or deluge systems. We look at those deeper in some other chapters. Remember, we use foam or dry chemical for fighting hot oil or Class B fires, right? And we'll learn the classes in other chapters. Chapter 19 also talks about unfired steam generating systems, two kinds, clean steam. If we need steam that's very clean because we're cooking food with the steam or cooking something that we don't want any contamination, we use what's called a clean steam generator. Unfired means we're using waste heat. So another unfired system is called heat recovery or HRSG, and we'll talk about what that means. Steam generated from a heat source that's excess. So when different plants talk about having a cogen installed, this became popular. It was starting to become popular 20-some years ago, 25 years ago, became very popular in the last 10 years. Plants create a lot of heat, and a lot of heat is just literally thrown away to the atmosphere. A lot of money can be saved by generating power or using that heat. So this is one of the two of the methods for using waste heat. Clean steam generators, we need very clean chemical-free steam. So we generate steam with deionized or distilled water. Examples for humidification, sterilization, vacuum systems, direct heating, and usually we talk about food processing when we look at clean steam generators. So there's a couple of waste heat boilers that are creating clean steam. The other one we're going to look at is heat recovery, HRSG. Our popular name or common name is HRSG. We call it a HRSG, HRSG, heat recovery steam generator. In the case of a gas turbine, we have a fairly inefficient piece of equipment. We're using it to drive a generator and create power. Normally would have a lot of waste heat going to the stack. By recovering heat from the stack, we can create some more steam to generate more power. Okay, so here's our steam turbine. Exhaust gases from the turbine are going into a HRSG unit. If you've seen one of these things, they all look pretty much the same. We've got hot gases coming in. We've got a high pressure section and a lower pressure section. Create a bunch of steam. We can drive another turbine and generate more power. Okay, and then we have coolers, exhaust going to the stack, and the gas turbine has an efficiency, overall efficiency. I'm just going to make up some wild numbers. Gas turbines are 45% efficient for fuel use and power creation. With a HRSG unit, heat recovery, steam generation, we can increase that efficiency by 15 or 20%. Thermal, so a review of this chapter, thermal fluid replaces steam or water in a hot oil system. Okay, if we have a hot oil system, we need to have a low-cost fluid with a high flash point because fire risk is high. Also, for cold weather use, we want a low pour point. Okay, these ones are not the best choices. These are the thermal fluid that replaces steam or hot water. Oil fired heater temperature control senses the temperature at the furnace outlet. For draft control, we have burner air registers and a stack damper. Hot oil temperature control depends on the firing rate, so we control air and fluid, control air and fuel to control the temperature, maximum temperature on our hot oil. Common combination of heating coils that makes hot oil units more efficient is the radiant and convection combination. Remember, when you have radiant and convection, radiant is surrounding the flames in the furnace. Convection tubes are in the top or the upper breaching area. Fired heaters are where? In the hot oil system.
Floor of the furnace.
On the floor. Okay. Spilled oil containment, concrete walls or dikes around the heater base. Okay. Automatic shutdowns are called interlocks. Okay. Low oil flow shutdowns on the heater oil outlet. Stack high temperature might mean what?
Ruptured tube.
Yeah. Safety discharge returns to the surge tank. Okay. Overheated oil. Oh, what's the problem with overheating the oil? We're gonna plug up the tubes with coke. This type of system has carbon steel piping. And to fight a fire, don't have a leak and at the start of it. Keep the system leak free. If you suspect coke deposits, we're going to do x-rays. Clean steam generators use what?
Distilled water.
Distilled, thank you. And that might be called water with no chemicals. Clean steam is generated from, also might be called deionized, okay? Three more slides. HRSG or HRSG usually looks like this. Oops. Lost that. And is called heat recovery steam generator. All right. And what does a heat recovery steam generator do? Recovers heat that would normally be wasted. Hot oil circulating pumps must be capable of high temperatures, designed for high temperature. One more slide. Best hot oil, most efficient hot oil heater system has combined radiant tubes in here, and convection tubes in the breeching. Okay. That is all, folks. I need to that, I can discard that. And I can stop recording.